get through everything. So welcome to our tutorial on deep learning for NLP. So I'm Christopher Manning from Stanford University, and let me just quickly get the other co-presenters to introduce themselves.
Hi, I'm Richard Socher, also from Stanford.
And Yashua Benju from University of Montreal.
Okay, so we're tremendously excited that all of you guys could be here today to hear our tutorial about deep learning. And we see this as really a great opportunity for you guys all to learn some stuff about what's really one of the most exciting and interesting new areas of natural language processing and machine learning. And in particular, what we're really hoping is not just that you'll learn a little, but that you'll be able to take what you learned here today and go home and actually start doing things with deep learning, and that this could be a really good opportunity to get in on the ground floor of what at the moment is only a very small group of people working in this area, but one that we hope can really expand. Now, admittedly, you'll probably have to read one or two papers as well as listen to this tutorial before you start writing your research papers. But we're hoping that today we can really explain some of the fundamentals and that you guys can really actually understand what's going on. So to that end, if people have any questions at all, do feel really free to ask questions. No questions too dumb. We'd really like to help people out with any things that they don't understand and would like to. The one exception to that, especially for the kind of beginning intro part, is if what you have is more kind of discussion, comparison, what-if-y kind of questions, we actually have a section towards the end where we sort of talk about some of the pluses and minuses, and that'd be better to leave till that part. But if it's understanding questions, do feel free to ask them, please. Okay, so starting at the very beginning, what is deep learning? And I'm going to explain that by contrasting it with most of what happens in machine learning. So in general, in current machine learning as used in NLP, that what we find is that we have human-designed representations and human-designed features. And largely, machine learning works really well because of that. So the actual machine learning part is basically doing numerical parameter optimization that's setting optimal weights for features. And computers are very good at doing that for us, but machine learning is really doing nothing more than that. So in contrast to that, the burgeoning area of representation learning is the field of attempting to automatically learn good features and representations to really try and move machine learning to doing much more. And within that general area, deep learning in particular is the approach of attempting to learn multiple levels of representation of increasing abstraction and complexity. So this is a canonical picture of what the deep learning systems look like. And so at the bottom, we have an input layer where we think of that as roughly raw sensory inputs, maybe not quite in fact, but roughly. And then our model will move up through progressive layers, which will learn more abstract, more useful representations of the input space. And then what happens right at the top depends on the task. What I've shown in this picture is a classic supervised prediction task. So at the end of the day, there's this one output unit that is making some kind of prediction that might be other things. So in general, deep learning has mainly explored deep belief networks, which are Markov random fields with multiple layers, like in this kind of picture, or various other kinds of multiple layer neural networks. So the very first section of the tutorial is going through with you guys a bunch of reasons for why you should be interested in exploring deep learning and should go off and try it for the rest of the summer. And so these are the big picture motivations. So the first one is the idea I've really already mentioned. It's this idea of learning representations and features. So handcrafting features is time consuming. It suffers from problems that the features that you come up with are normally both overspecified and incomplete. But perhaps more seriously than either of those problems, the problem is that you come up with good features after you've spent a couple of weeks doing it that are really good for the data set you trained on. But then you need to, each time you move to a different task, a different domain, a different register, a few years have gone by, that you then need to be redeveloping systems for each of these cases, and the work never ends. So what we'd like to be able to do is move beyond these simple machine learning combined with clever human handcrafting of systems. So if you look at what humans do, well, humans develop representations, that when we're confronted with new domains, that we develop representations that allow us to make sense of the domains. And we'd like our computers to do the same. And deep learning is one of the most promising ways of going about doing this. Okay, the second motivation is, again, one of contrast with how we do things these days. So at the moment, by and large, NLP systems use these atomic symbol representations, commonly known as words, and other such units. And because of that, the systems are incredibly fragile. So here's one little example of this, and this is actually taken from the Stanford parser, so I'm not disparaging anybody else. Here's a simple sentence: my dog also eats oranges, and it gives it a perfect parse. And now I change oranges to bananas, and the parse suddenly gets messed up in a really weird way. Now, if you've spent lots of time staring at the pen tree bank, you can understand why this is. It turns out the word bananas only appears once in the pen tree bank, and the usage "go bananas." So there's a perfectly rational explanation for why the parser messes up. But this just shouldn't happen. That we should understand something about bananas and know that we should be parsing it like oranges in a context like this. Okay, so we want to fix that problem. So in contrast to that situation, something that's been incredibly successful in NLP is the idea of making use of distributional similarity models for learning about similarities between words. So in general, this just always helps your systems enormously. So classic techniques like ground clusters or Nye exchange clustering, you can take those kind of distributional similarity representations and throw them into any system, and they improve the system enormously. So for example, in the Stanford NER, you can lower the error rate by about a quarter of the distributional similarity features. So that's marvelous. But what I want to argue for today is doing something even more marvelous. And so we want to make this contrast between having distributional similarity representations and distributed representations. And that's what's tried to be indicated with this picture here. So this over here is the picture that you get if you either have straight hard clustering or something like nearest neighbor representations. So for each separate little point in this piece of the space, you have to be learning something separate about each piece in the space, each cluster. And so that stands in contrast to the picture on the right, that's labeled here multi-clustering. So on this side, what you do is that you've got features that are not mutually exclusive, but that cross-cut the space. And if you have these kind of cross-cutting features, which is equivalent to saying you have a distributed representation, so for each input, you've got a representation of it across multiple units, well, then you have a model that can be exponentially more efficient and powerful. And that's because now we're able to cut this space into 7 pieces with just 3 features. And we're getting roughly an exponential increase in the number of power. So in precisely that sense, distributed representations give us a way of dealing with this classic curse of dimensionality. So if we just have hard clusters or nearest neighbors, we have to have examples for every little point in the space, which is growing exponentially as the dimension increases. And so this has been a huge problem for machine learning. And there are other solutions to this problem. So one classic solution is manual feature design. So for manual feature design, we basically by hand specify what are the dimensions on which you're allowed to generalize and treat things as the same. You can get generalization by assuming something like a linear model, like a linear regression model, which tells you how you should be able to generalize. There's been a lot of work in kernel methods, which will also give you a basis for generalizing. But in this space, neural networks are a very promising method, because they give you an automatic method to parameterize and then learn a similarity kernel, which will be appropriate for different tasks. This is the third motivation. And so this is a motivation that you hear a lot, not only in talks about deep learning, but deep learning is really one of the very promising ways to address it. So at the moment, Most good NLP and machine learning methods require label training data. We do supervised learning. Now, of course, there's a massive amount of work on unsupervised, semi-supervised, etc. But if you just think about the tools that we really use and that work well for us, all of the statistical parsers and the NER systems and things like that, they're trained as supervised learning by and large. And that stands in contrast to the fact that almost all data in the world is unlabeled. And so we just have to be acquiring most information unsupervised. And what we hope to show you in the later parts of today is that we can do this wonderful thing whereby building a good model of the observed data, we can use that to really, really help us make classification decisions with a little bit of supervised data. The fourth motivation for deep learning is this idea from which the name deep learning comes, the idea of learning multiple levels of representation. And so the origins of this are biologically inspired. So it seems that our brains have a generic learning algorithm that they can use. And in particular, they appear to have a deep architecture where you have multiple levels of processing. And so this has been explored most thoroughly in the area of vision, where you're starting off with the lowest level V1 edge detectors, then V2 has primitive shape detectors, and then you move into V3 and V4, and you start to have increasingly high-level visual abstractions. And so the hope is that we could do something similar inside machine learning. And the idea here is what we'd like to do is build intermediate representations which are useful for tasks. And in particular, we hope that we can use them for multiple different tasks, and so we get sharing. So having multiple levels of latent variables allows a combinatorial sharing of statistical strength. And this is another way in which we can gain an exponential gain in efficiency. Because if you have insufficient depth of the model, like in the kind of typical linear models we use in NLP supervised classifiers, that you're ending up with these exponential numbers of features to cope for the lack of model depth. Here's a nice picture of how it can work with learning multiple levels of representation. So this is a deep learning model that was built by Hong-Lak Lee, Andrew Ng, and other colleagues at Stanford University. And so this is learning representations of pictures. And just in the New York Times earlier this week and other newspapers, there was the latest iteration of this work that was being done with images of Google that you might have seen the article. This was from a couple of years ago version. But what you can see is that this is a multi-layered network, and it really is the case that the model in a completely unsupervised way is learning these progressive layers of representation, somewhat like the human visual system. So at the first layer, we're basically getting edge detectors and lightness and darkness detectors. At the second layer, we're then getting face parts. We're getting eyes and noses and mouths and things like that. And then at the third layer, we kind of get these kind of abstract face spaces. Some work has been done doing the same thing with language representations. So in particular, they've also looked at doing this with speech representations. And these are kind of turned sideways, the pictures. But you can see that the first level pictures look kind of like what you see in your spectrograms, that we have formant features and have harmonic features. And then the second layer is the more abstract representation, and it's hard to see how to think about that. But once we move into the higher level linguistic representations, we then have a third special kind of problem of dealing with multiple levels of representation, and that's a special feature of human languages. So human languages are composed from pieces. So you have words that are built into phrases, which are built into clauses, which are built into sentences. And so to deal with that, we really need to build compositionality also into our machine learning models. And the central idea for doing that is this idea of recursion. So in the simplest cases, we can just be repeating copies of the same operator with the same parameters that are applied at different points in the sequence. But in a more sophisticated way, we can be building up more complex structures like tree structures. And that's a topic we'll talk about a lot in the second part of this tutorial. Okay, then the final motivation is the why now motivation. Those of you who have who are on the older side of the audience or who have read your history books will know that neural networks were popular in the 1950s and they were popular again in the 1980s. And you might be wondering, is there a reason to go back to them now? Now, of course, you could think there was a pattern there. They become popular every 30 years. So in the 2010s is the right time to be looking at them again. But there's a more profound reason than that, and that's the following. So despite the fact that a lot of the algorithms for neural networks, including the algorithms we'll show in more detail today, were actually worked out well in the 1980s, that until 2006, people just weren't able to successfully learn deep models. It just didn't really work. And that's why, if you remember back to 1980s neural networks, that effectively there was always just this one hidden layer in the middle because it wasn't effective to have more. But since then, in the last few years, some things have changed. The biggest one, and that's the one that's being dated to 2006, is that people, originally Jeff Hinton, developed new methods for unsupervised pre-training, which have made it possible to successfully learn very effective deep models. And so that was initially the work on restricted Boltzmann machines, which actually we're not going to talk about in detail today, because it then turns out that other methods that have been found that are as successful and are perhaps easier to think about and work with. So we will talk about other methods like autoencoders and contrastive estimation. There have been other developments as well, some of them paralleling general advances in machine learning. So the fact that we just have better understanding of how to do model regularization and have come up with more efficient parameter estimation methods have already helped. So because of these developments, it's already the case that there have been some very successful results in using deep learning models in human language technology applications. I'll just show you a couple right now, and then you'll see a bunch more as we proceed through the tutorial. So one very impressive example is in the area of building language models. A simple area, but nevertheless core to so many of our natural language processing techniques. So I think it's fair to say that the field of language modeling was essentially stalled for about a decade. So there was the development in the 90s of Knesset smoothing, which was very successful, led to a new level of language modeling performance. And everyone for the last decade and a half has just been building Knesset smooth language models with progressively more data, which then allows you to do progressively bigger n-grams. And so we now normally build our 5-gram Knesset smooth language models. And people have tried other things, but it's been very hard to get meaningful gains beyond that. So in the results over here on the right, so here's our Knesset baseline, and the second line is showing you a discriminatively trained language model, a maximum entropy language model, and it's a teeny bit better than the Knesset model, but very, very little better. These are word error rate results from the speech recognition system. So from that perspective, it's really, really exciting that over the last few years, using neural language models, that people have started to get really impressive improvements in language model quality that lead to huge performance in speech recognition and other applications. So in the example here, this is work from Mikolov and his Hungarian colleagues, that the neural network model is then lowering the word error rate by 2.5% absolute. So that's something like a 16% word error rate reduction, which is just a huge, huge performance increase. Not only in the area of language modeling, deep learning models have been extremely successful for speech recognition applications. So the results that are being shown here are work from Microsoft Research by a bunch of people. So here we see on this line is the baseline, which is sort of standard good speech, 40 Gaussian mixture model, discriminative maximum mutual information training, trained on 309 hours of switchboard, and so that's giving these kind of error rates in the mid to high 20s on switchboard and Fisher. And so then in the middle line, it's taking exactly the same training data, but it's training deep 7-layer deep neural network with enormous reductions in error rate. So the word error rates are going down by about a third, huge gains. And in fact, that